So, coming back to 11.5, because are there any other questions over 11.4 that before we escape that section?
Just there is a question in 11.3. I think they want us to do the steps. They give you they want L.
Which one is it?
54.
Oh yeah, we did that. That was the one about finding the distance between a point and a line. We did that last time. Somebody had a question about it. And we basically did all the steps, if I remember. Well, we did most of the steps and then I left the last couple for you guys to finish up.
Do we have to go with the steps themselves, or we just like?
Now, I'll tell you what, I mean, basically that's got A through E, you've got to do those. But if you think of a different way to do it, then you could do it that other way. And see that it comes out to be the same answer. They're stepping you through the way that they say that it could be done. It's not saying that that's the only way it could be done necessarily.
Okay.
I'd be really interested in seeing another way to do it. Okay. So I was about to say in 2D, you have this guy, and you have this guy, which is basically the same thing, right?
Yeah.
Just the B has been spread amongst all this other crap. There's your MX, so then your B must be all the other stuff put together. All right, nothing amazing there. Now we're talking about in any dimension above that. Any dimension above that. And actually equal to 2 also. And actually equal to 1 too. Let's just think of that. It's got the same form, except now slope is very difficult. In 2D it's easy. Slope just becomes a ratio. Because I have 2D, two things. Y to X, right? The change in Y, change in X. In 3, 4, 5D, you can't make a single ratio that makes any sense. Right? You'd have to have some kind of a running 3 to 2 to 1 weirdness that doesn't look good when you're trying to make an equation out of it. So now, instead of using just a single number to talk about direction, we use an entire vector to talk about direction. So it's got a very similar format. But I'm hoping something jumps out at you. I can't remember how much I said about this last time. So I'm going to try to put the same form here. This is a little different form than what I did last time and what the book does. I'm just kind of forcing it in that form. Y equals mx plus b. Y equals mx plus b. What's my true variable up here? So what does it sort of feel like? Where else do we use t? Sort of doing that. Yeah, parametric. So look at this component-wise. Let me write this guy component-wise. So what this is trying to do, and somebody pointed this out to me after class last time. We are referring to points on a line as position vectors that point to those points. Are you with me? So that's how we're going to describe a line now using vectors. This R of t is always pointing to the line. Oh look, there it goes. You know, that's what it's doing. So that's how we can use these vectors to help us out. So this is any arbitrary point that this thing is pointing to. How do you get there? You start here, and you go this much of this. Now that is very technical what I just said. You start here, and you go this many steps of this. Right? And then basically here, you start here, and you go this many steps of this. Right? Same thing. So break it down for me component-wise. The x components only. What does that function look like? What does that formula look like for the x components only? AT plus x naught. Let me turn that around, x naught plus AT, so it looks more like what I'm used to. Y equals, incredibly enough, y naught plus BT, and z equals z naught plus CT. So a lot of your parametric equation background, which for some of us is a little more rocky, a lot of that, not a lot of them, you're not freaking out too much, but you can certainly do, there will be a few problems that make you look at this as if they are parametric equations, because that's what they really are. This is just a reformulation of a bunch of parametric equations. It puts it on a single line instead of 3. Really, right? And if there are only these two, how could you unparametricize it? What's the procedure?
Eliminate the t.
Eliminate the t. Solve for t and do it. Why is it more difficult once they do that? Is there any way to really do it? You can eliminate the t, but then you got two other equations you have to plug it into. You guys kind of with me here? A little bit. So in 2D, I get y in terms of x directly. In 3D, I can't possibly expect that to happen for me. I've got too many directions for the. I'd have to create a 3-sided equation, and I'm not going to make that math up right now, right? Okay, maybe you guys are with me a little bit. Now look, I really want you to look at the idea here. In fact, can you guys, what points would this line go through? This line here. And I'm not being overly specific. I don't mean list all the points. Give me some example points that this line goes through. How do I know this is a straight line, by the way? All right, so I like the beginning. We know it's a straight line because all the t's, I mean, they are all linear equations, aren't they? Your points are linear equations of the parameter t. If I start squaring any of these, we're obviously going to get that bend to things, right? And we're back in good old parametric equation realm that we're used to. But here, for example, if t equals 0, you get the point -1, 3, 0. So I can think of that as my starting point, if I want to, right? That could be the point x dot, y dot, z dot. How are we doing so far? Sort of like my y-intercept. In a sense, this is sort of my, well, it's not really an intercept. We'll just leave it at that. And then if t equals 1, yeah, you get 3, 1, -1, and we could do this all. Incredibly enough, right? How are we doing so far? Okay, all right, all right. So what can you do with these things? So this is how you get the equation of line. So let's actually do some very simple problems that sound very familiar. One of the most famous line problems from algebra is find the equation of a line that goes through these 2 points. All right? So let's do it. Here we are on calculus 3, going back 2. Find the equation of the line. Going through 1, -1, 4, and -2, -1. Let's not make it. Let's see. -3, 1. Sure. I like it.
Just give that problem to little brother.
What's that?
I should give that problem to that little brother.
I like it. And just see what the hell he does.
Like, what the heck?
Watch his brain explode. Yeah.
Professor, those are just points for t equals 0, t equals 1. Those are just
Yeah,
points.
and in fact, if they don't describe to me, if they don't tell me what t is between, then obviously this is the entire line that I'm describing here. This is all the points corresponding to any value of t. Some of the problems will tell you t can only be between 0 and 2 pi or something, in which case you're going to create a line segment, right? If I start somewhere specific and I end somewhere specific, I'm not going to go in infinitely in either direction. It's just going to be a line segment. Cool. Okay, maybe. Such a wide variety of looks on your faces right now. That's crazy. So how the hell are we going to do this? This is the way that I taught my algebra class, or teach, because I'm teaching one of these right now, is I tell them anytime you see the find the equation with a line that does something, you've got to find 2 things. It's the same thing as algebra as it is now. You've got to find a direction, which in algebra would be slope, and you've got to find a point that it starts at. Well, we got the freaking point. We got 2. So it doesn't matter which one we use. Doesn't matter which point I use in my equation. No, think about it. Of course it doesn't matter. If I use one, I go take a step back and I can get the other, or I use this guy and take a step forward and I get him. It doesn't matter which one I use. My t is just going to be giving me different things at different times. Eventually I get the whole damn line. Who cares? So which point do you guys want to use? The first one? The one with the yellow ones? Alright, I like it. And I need a direction. So how do you get the direction piece of this? I like it. You know, how do you find the vector? The vector that's where? Between the 2 points, and how do you find that? Hopefully you know how to do that because that's the first thing you have to do in the quiz.
-3.
Yeah, so the direction will be the vector that's between the given points. It doesn't matter, and again, it doesn't matter which way you subtract here. Because what multiples of this vector am I going to use? Positive and negative. So if you subtract one way or the other, who cares? You're eventually going to go the other way once you put negative t's in, positive t's in. How you guys doing so far? So the direction, you will get, the funny thing is very often in calculus you got to realize when I say direction, I really mean direction not truly just that way, but this way also, along that one-dimensional line there. That's the true direction that we're talking about in this case. Because you can have negative multiples of it going the other way. So I don't care. I'm going to do it where I get a positive first, just because. And I get the positives all the way through. Sweet.
Professor,
If I did that right. Yes.
did you arbitrarily choose 1, -1, 4 as your point?
Totally. Because again, if I gave you this problem in algebra, find the equation of the line between these 2 points. First you'd find the slope, y 2 minus 1, blah, blah, blah. And then you get a point to plug it in here, right? Doesn't matter which point you use. Of course it doesn't matter. The slope can go from this point to the other point, or it can go back. He doesn't care. So we inherit that property here. We have more dimensions, but the ideas don't change. I still need a point. I still need a direction to go in. Does it matter if somebody uses the other direction? No, because their negative multiples will take it back to the other way. Who cares? Yeah.
So you can essentially parameterize the two-dimensional equation as well.
Yeah, exactly. Everything we're doing here, we could also do here. Cool? Because these I could look at, I could find a vector that goes between these two. That would be my v. I could use either one of them as my starting point. So the whole thing we're doing here works here also. That's why earlier I put it there. N greater than or equal to 2. Okay. So how do I finish this out? R of t equals what? Here's where you got to be a little careful. Here's the point. What's the position vector associated with this? Yeah, 1, -1, 4. Just change the symbols. Okay. So my vector initially points, my R of t initially points here. That's where it starts. And then it's going to move, it's going to point to other points, but they're going to have to follow this direction. I'm going to start there and I'm going to go.
Right, so the position vector is the same as the points, or is it different?
No. I'm sorry, say again. The position vector, yes. The position vector like we know. In when we're not looking at it vector-wise, I treat it as this point. If I want to use vectors, the vectors now point to those points. Right? So the idea here is I have this line going through space. R of t, here's the origin, is pointing to all the points. Oops, let me go over a little bit. That's the idea. Is R of t naught, R of t1, R of t2, whatever. That's the idea. So I'm pointing at all the points. So let's finish this out and then we'll plug a few values in here and think about what that means. So now I start at this point and go this many of these.
would be the,
This would be B,
yeah, right,
this would be M, and this would be
the-
X.
The variable. yeah.
The variable. I love it. Cool.
So that's all it is.
Yeah, that's it.
That right there.
I mean, that is the phrase I want you guys to be sort of thinking in your head. That ain't that bad. That is not that bad. It really isn't. It's not that big of a stretch from what you did in algebra. It really isn't. Yeah.
But now those points, because you're writing them like that, become vectors?
Exactly.
Okay. So you put in.
So this is what's called a vector valued function, as opposed to a scalar valued function. When you throw something in there for t, your answer is what physically? It's a vector. Cool. Now lines are supposed to be composed of points, but we have chosen to look at them as these little, from the origin out, these pointers, these vectors are pointing to the points. Is that really that big of a difference? No. So it's sort of arbitrary the way we did it in the first place. We decided here, we'll do it like this. You throw in an X, out pops a Y, there you go, Jeff, and we'll put it together. But this is so ingrained in your head, you don't realize that that's sort of arbitrary how we decided to do that to a point. I mean, that's 2D is not too much flexibility, but still. So why couldn't we instead say, like here, we say, no, it's not just sitting there in space and I put it together. It's a vector pointing to somewhere in space. And then my line kind of, as I go along my line, that vector moves with it. So that vector describes the line in space. So if I have some line that's kind of doing like this, then my arm is the R of t. That's my origin's got to stay the same place. But it's kind of hard to do that. So that's all this thing is doing. It points there first, and then as I move t, as I change t, it points to other things on that line. So it's pointing to my line the whole way. Okay, cool. And this is really, mathematically, this is just a reformulation of a set of parametric equations. Not a phrase you say too often, but there it is. Yeah.
And since we started out with an arbitrary decision, I guess you could say, does that mean that the other vector value, that is also arbitrary?
How do you mean? Sorry, this?
Yes, the 3, 2.
This is not arbitrary. Where did this come from?
If it came from the difference.
And the only arbitrariness to this is it could be -3, -2, -3.
Yeah,
But then you just change all your t values, just change the signs, and it's the same stupid thing, right? Cool. Watch this. What does t have to be to capture this other point? To point to that other point?
-1.
Yeah, t's got to be -1.
Well done.
Really? Oh, yeah.
It's just changing.
Something went freaky there.
Oh. Yeah.
Well, no, because it'd be t is -1 and be that point plus 1 -1.
Should be the way that we set this up. Let me think.
Yeah.
Yeah, -1.
You're right. You're right.
-3, yeah. -3, yeah. Is that understood? So if I would have chosen to use this other point instead, here, it would have been the same thing, wouldn't it? I mean, it would have, if I had chose that other point, then the line would be this, plus t times 3, 2, 3. These two are the same thing. And it's a little hidden here. I really desperately want you guys to understand that. Is this the same as, are these the same equation of a line? Now this is really easy to see that, but when I tell, of course, my math 90 students, some of them say no, but then, you add that forward. But it's procedural. They think it's totally different. Well, this one I did this way, and this one I did with a y-intercept, and it's different. No, of course it comes out the same. Here, it's a lot harder to see the math inherent in here. This is 1 plus 3t. Who cares what number is really here, as long as multiples of t bring back the points they're supposed to bring back. So mathematically, it's not a big mystery. It's a little harder to see than this. This is just solving a stupid equation, right? It's a little harder because the math is sort of in here. So I can change the numbers here and say, well, that's the same line. Those are the same lines. Because that line goes through both of these points. Who cares where you start? T is just going to be, T equal to 1 is not going to give the same point as that one, but do you care? Do certain points have to happen at certain times? I don't care. As long as you get all the points on that line, I'm happy. So here, T equal to -1 gives me -2, -3, 1, right? Here, T equal to 1 gives me what?
1, -1.
Yeah, 1, -1, 4. And T equal to -1 gives me something else entirely. But you can figure out what T would have to be here. If I put T equal to -1, I get what? -5. You can do it, Jeff. -5, -2. Cool? Could you figure out what T has to be here to get that same point? You're guaranteed that a T exists for that because they're both the same equation of the same line. Cool?
Maybe.
So on one level, the math involved behind this is nice and easy math. It should be math you just can jump on because you guys should be good playing with numbers. It's really what this determines is, can you just play with these numbers? Okay. Oh, let's see. I have notes or something. Oh. We're just going to do a little bit. We're not going to have a full class, just to let you know. I'm going to leave pretty soon. One thing I do want to show you on the overhead. Let me let you guys try this problem out here. Turn it off.
It turned off. Yeah.
Oh yeah, he's decided he was on for too long. Poor Louis. Let me try you. Yeah, it's on. There it is. Now, I'm putting it up here because, oh, that one now is decided. Oh, yay. Alright. I'm going to play with my emotions as long as you eventually go on. So obviously, and I keep forgetting to bring isometric paper in here, so next time, there are a few problems in your homework where you have to graph some things in 3D. So next time I'm going to bring in some isometric paper, we're going to do a few problems together and show you how the paper works and how it makes it a lot easier to see things. So here's basically the same problem we just did with just different points. So can you guys go ahead and take a minute to figure out the equation of that line? Here's what they're looking at. Find the equation of that line there. Okay. Here they are, working away. you guys way back over here and put it over 3. A little easier to see. Alright, so you guys, see how far along you got. What's your directional vector?
10 minus 3 minus 7.
Do it one more time.
7, 3,
7,
Minus 3 minus
7, negative 3, negative 9?
7. Yeah.
Okay, cool. Or negative 7, 3, 9?
Yeah.
Anything else did it the other way? Doesn't matter.
Does it really, like, since it has, like, T0 and P1, is it?
Yeah, it depends on the way that I word the question. So I could say, if I would have said find, you know, using this or something, I'm not sure how I'd put it.
Point something.
Because my point's always it doesn't matter. So to me, I hate directions that go against the idea that it doesn't matter. So why would the directions tell me? You know, and I know what you mean. They kind of make it seem like you have to do it one way over the other. But the concept is, no, it doesn't matter. So I want to reinforce the concept. So I would never really do that to you.
Okay, so
So
it doesn't matter.
it doesn't matter. That's the concept. So I don't care which way you got it. Either this or the negative of this. And the point, the position vector, and again, you got flexibility there too. So I don't care. Let's use this one. Just because.
And yet again, it doesn't matter. Unless you
Exactly.
specify, like, the point of this, the direction.
Yeah, unless I for some reason said you must do this or something. There will be problems where I only give you 1 point, so then there's no, you gotta use that 1 point. So what's the formula for this? What's the equation? 4, 2, negative 1.
Plus T7.
Now write it for me in the other format. What would it look like in the other format? X equals,
negative 3, 5.
Oh, 4 plus 17.
oh yeah, 4 plus 17. Y equals,
5 plus
2 plus.
that's a 2 here, right? Oh, you used, oh yeah, you used the other one, so it doesn't matter. So using this one, I get 2 plus, 2 minus 3t, sorry. And z equals negative 1 minus 9c. Now notice these numbers, if you used, it could be negative 3, 5, 8, right? If you use that point here. And this could be minus plus plus if you decided to go the other way. So you can imagine grading is sort of a nightmare here, but oh well. Too bad for me. Here's the interesting thing. If I asked you, and I'm going to be a little evil here because I've got a few minutes here. If I asked you to find the angle this line makes with the XY plane, that would suck. And I wouldn't blame you if I was a student sitting here like, please don't do that shit. But can somebody imagine how you might start to do that? And why do you have to be very specific here? There's only one angle that it can find with the XY plane. There's only one. So if this is my vector, what's the angle this vector makes with the board? Is it the angle over here? No, it's the angle where it's leaning over, right? Directly over its component in that plane. You guys with me so far?
Yeah.
I want to make sure everybody's with me. Mathematically, this is an interesting question. So the more interested you are in pure mathematics, the more interesting this question is, yeah.
So you only find the angle in the direction of its projection? Like
The
this?
angle related to the direction. So here, this guy's projection would be maybe like this. Right? If I were to smush him down into the XY plane, that's his projection. So I want to look for that angle there. Because how many angles are there with the XY plane in general without that kind of definition? There's any number you want. It could be related to what? vector in the xy plane, Jeff. There's a million of them. Billions. Infinite. But yeah, it's got to be with the projection in the xy plane. Now there are two ways to get that projection. And you guys right now have the projection formula, maybe not perfectly there, but you're thinking, oh shit, that thing kind of sucks, and oh god, and, right? The beautiful thing about this, what's true about the xy plane? What's sort of the definition of the xy plane? Z is 0. So kill him. Right, so to find projection in xy plane, z equals 0. So what are you left with? This and this, right? Yes, sir.
When you say z equals 0, do you just completely disregard that equation, or can you set actually z equal to 0 and solve for t?
That would be too specific. We really do just want to kill z. Sort of like truncating. You never want to truncate. You always are around, but sometimes you might want to just truncate. This is one of those cases we're not solving for what t makes z 0. We're saying we want z to always be 0. That's the difference. So I don't want to have t be a specific thing. That would give me this point, like roughly here, right? That where it hits the xy plane.
Yeah.
I don't want to be that specific. I just want to replace this with 0. So these two are still in effect, right? And I'm hoping maybe a few of you guys realize there's an easier way to do this problem. Let's go with this for a minute. Now we're back into our good old parametric stuff. How could you find the equation? Yeah, eliminate the t. But here's a more, well, let's do that.
3 seconds.
So t equals, what do we get? 2 minus y over 3. So x equals 4 plus, I'm not sure why I did it that way, but oh well. Let's say 14 minus 7y over 3. Just solve for t and then plug it into the other one, right? And that looks disgusting. You can solve for y, whatever. That's nothing major there, right? You guys could do that. Eliminate the parameter between two linear equations. Ooh.
Okay.
Right?
Can we use the dot product for this to find the angle?
You could use a dot product to find the angle, but notice my question had nothing to do with the angle necessarily. My question was just find the projection. You could use a dot product, but to use the dot product, you first need a second vector. So what we're actually doing is, we've sort of found that second vector in a roundabout way. There's the equation for all the points that kind of lie on that second vector direction. Here's the direct way to do this. What's the projection of this point in the xy plane? Let's see. 4, 2, I love it. Or 4, 2, 0 to be specific, yeah, but 4, 2 in the xy plane, I love it. 4, 2, 0. And that point? So if I just project the points, I get 4, 2, 0. And we'll just say 4, 2 because now I'm kind of like in the xy plane. Is that cool? And now I forgot it. Negative 3, 5. And couldn't you find the equation of the line between those 2 points? So it'd be y minus 5 equals x plus 3. The slope is 3 over negative 7. That sounds kind of familiar. You guys with me? What happened to t in there? Should be a y. Negative 7 over 3, see that? Because I got to solve for y. So here's my equation, y equals negative 3 sevenths x. Let's see, minus 9 sevenths plus 5 is plus 26. It's not, I can't even think of it. Minus 9 plus 25. Plus 25, Jeff. Minus 9 sevenths, oh yeah, minus 9 sevenths plus 35 sevenths is 26 sevenths, right? Yes, cool. All right. Yay. And if you solve this one for y, you'll get the same thing. Multiply by 3, add the 7y, 12 plus 14 is 26. I mean, you'll get the same thing if you solve this for y. I'm desperately hoping some of you guys realize what just happened. This is a very direct way to do it. Just kill the point, drop the points directly right into the xy plane. And that relates exactly to, what's this guy's projection? What's right beneath the dude, right? You don't even rotate. I really want you to realize this. I'm not rotating that line, because that would be wrong. I am just smushing that line, right? I just want this component of the line that lies in this plane. Okay, wow. That's enough. Told you we get out earlier. Oh, one last thing. Do this at home and bring this with you next time. I'm asking you to read ahead in 11.5.
No, no. You can raise your hand. There's something last. Yes, I'll let you know.